Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in this particular video you might be wondering, why are you actually looking at this particular type of compounds in here and what makes them actually unique in this particular case. And so this actually comes into play when dealing with what we notice where we see some rings, and these rings here we're going to be dealing with here is called saturated type of rings that are in this case heterocyclic. And so is saturated, which means that involves we focusing on not the straight type of compounds, which in this case is going to be looking at flat compounds like rings aromatically, but instead we're going to be looking at mainly sp3 hybridized states, compounds that are actually bent. And so by looking at non-flat rings, we are going to be focusing in here on the rings that may lead to the formation of bonds that involves compounds that has either the following: we have carbon, we have maybe oxygen, maybe we might have nitrogen or sulfur that are present around or within the rings that in this case is known to be heterocyclic compounds here. And so this is actually going to be focusing in here based on what we have in this particular example. In this case here we see oxygens in a saturated ring, and what we notice is that we have a three-membered ring in this particular compound that is called oxyrane. And another one here is, in this case we are having a four-membered ring, and this four-membered ring that has oxygen in it is called oxidane. And oxidane is another one that is quite different from this particular one right here. And the next one here, looking at it, is called tetrahydrofuran. And this particular compound, what we notice is that the oxygen is in a five-membered ring, and this oxygen here, which is in the five-membered ring, is actually what makes it different in here from the other one, which has a six-membered ring containing oxygen, and this here is called tetrahydrofuran. And this here of course shows the transition going from a three-membered ring to four-membered ring to five-membered rings and to six-membered rings that has oxygen present, and it is having an hybridization that is sp3, which means that there is no flat regions, like for example there is no aromaticity around that particular system. And so next one here now is looking at the other types here where we see nitrogens, and what we notice is that we have a three-membered ring that has nitrogen present in there, which shows the heteroatom or heterocyclic form of this particular compound, and this is actually called iseridine. And the next one here is nitrogen present in a four-membered ring, which in this case is called aziridine. And the next one here, not looking at this particular aromatic ring that has nitrogen in it, but looking at this heterocyclic ring that has nitrogen present in it, is found in this particular compound, which is called pyrrolidine. And finally here we have our heterocyclic compound that has nitrogen present in the ring, and this ring here makes this whole compound, which is shown to be present in piperidine. And these are all the interesting types of heterocyclic aromatic compounds that you are going to come across. And you might be asking yourself, how is these rings, or how are these rings created? Mainly focusing on the heteroatom present or heterocyclic formation of these rings. How is this actually accomplished? This is accomplished by special chemical features of saturated heteroaromatic or heterocyclic that results in heteroatoms that makes ring easy to make by ring closing reactions. Like for example here, we are going to have one case where we have oxygen, or in this case hydroxyl, and here is a very long chain, and on one end we have a specific good living group, usually a halide, and we also have maybe in this case another one where we have the nitrogen form, and this nitrogen in this case is going to be called an amine, and this amine has a lone pair, and so it is attached to a particular bent compound, and at the end we have a halide that is a good living group. So in this case, what we notice is that due to the presence of the lone pair, we are able to perform a reaction which is similar to an SN2 reaction, where our oxygen lone pair forms a bond with the carbon, thereby causing this particular good living group to form a lone pair, breaking this bond and leaves. And it is also similar to nitrogen, which makes nitrogen and oxygen to be good nucleophiles in this particular process within this particular compound, and this will lead to the formation of any of these particular rings that we have right here, either being oxygen or in this case either being nitrogen, heterocyclic compound. So one thing specifically with an example is looking at MCPBA, and this is an exception here because this exception actually shows us that when this reaction is performed and it is done in the presence of a specific type of compound which has just double bond present right there, so in this case it is called an ethane. And so let's clarify this by writing it in a simplified form, where we have our aromatic ring attached to this particular carbonyl, and this is attached to the oxygen, and in here we have our other oxygen, and in here we have our hydrogen. And so we have our ethane actually coming in here, and what happens now is that our ethane, first off, is to notice that we have our oxygen which has a lone pair, and this lone pair forms a bonding pair with this particular carbon, thereby causing this particular pi bond to form a bonding pair between this carbon here and this particular oxygen. Now what does that result in? This results here in the breaking of this bond to form a particular pi bond between this oxygen here and this particular carbon, therefore causing this particular pi bond to form a lone pair on this oxygen, and this oxygen that has lone pairs here will then form a bond with the hydrogen, and therefore this leads to the formation of our specific product, where we have our aromatic ring to be attached to this particular form of a carboxylic acid, and this results in the formation of our desired product, which is a three-membered ring that is heterocyclic and has oxygen present in there, which is rightly familiar to the origin of this particular ring that is formed right here, oxyarene. So that is one thing to keep in mind based on MCPBA as the exception when it is reacting with an alkene, in this case ethene in here. So next one here we're going to look at is what are the favorable outcomes of the ring closing reactions that is eased, and this is actually in this particular order. The order is where we have first 5-membered ring to be in this case greater than that of our 6-membered ring in terms of the favorability, and 6-membered ring is greater than the 3-membered ring favorability, and this is greater than the 7-membered ring favorability, and finally this is greater than our 4-membered ring in terms of the favorability. And the question here is this: why is it 5 greater than 6? We're going to look at an example in this particular case right here, where we have nitrogen, and this case here we have specific good living groups that are the same, but what is different here? We have different number of branches. In this case here, we have 1, 2, 3, 4, 5, and in this case here we have 1, 2, 3, 4, 5, 6. And so what happens is that when we perform this same reaction here, there are in this particular reaction here, there are a couple of things that has to happen. In this case here, first is that to overcome the strain, to eliminate, what we have to do is first we have to rotate this bond in the clockwise direction, and this here in the counterclockwise direction, and this bond here in the counterclockwise direction in order for we to actually create our specific reaction at close proximity that will lead our good nucleophile to form a bond with the carbon here, thereby causing this to be a good living group. This shows that it has tiny strain compared to this particular other reaction here, where we have a particular case where we have to rotate how many bonds here. We have to rotate this one, this bond here, this bond right here, both in the counterclockwise direction, and finally we have to rotate this as well in the counterclockwise direction, which means here that this will have to be done in order for our nitrogen and our specific good living group carbon to be at close proximity to result in the formation of a new bond, thereby causing this good living group to leave. Therefore, while this particular first case here has a tiny strain attached because it is a 5-membered ring, but in this case here, this has no strain in this particular case because it has more atoms along the chain to facilitate this particular reaction. But hey, one thing we have to consider is the specific entropy. Take note that entropy focuses on the electronic states, and the electronic states and the bond strength are the things that are in play in this particular reaction, and this has to be the particular variables that needs to be taken into consideration in this particular type of reaction. However, in terms of entropy, we know that in this case we are going to be involving many number of molecules or number of particular molecules, and looking at the number of molecules, we also have to consider how many atoms are around a specific molecule. And in this case here, we notice that 5, in this case for A, we'll consider A to be 5, has or is faster than that of 6-membered rings. And the reason why is because while for 5 we have how many types of bonds that are dihedral, there are 3 dihedral bonds that will be involved in this particular reaction for it to actually be facilitated. However, for the 6-membered ring, we need to have 4 dihedral that will have to rotate, and this causes an increase in the entropy energy in here. So while this one will have a greater entropy for the 6-membered ring than that of the 5 in terms of the entropy, this shows that the 5 will have less dihedral that will then favor this particular reaction to be established compared to a 6-membered ring creation. So therefore, this is similar in terms of looking at 3-membered rings compared to that of a 7-membered ring. For 3-membered rings, in this case we have nitrogen here, and we have 1, 2, 3. So in this case we have a good living group. However, in here versus that of a 7-membered ring where we have a nitrogen, we have 1, 2, 3, 4, 5, 6, 7. For a 3-membered ring, we have only 1 bond that is dihedral that we have to rotate in order for this particular reaction to be facilitated. However, this one here will have, in this case, 1, we have 2, we have 3, we have 4, and we have 5. And where our 3-membered ring that will be formed here will have a high strain to bring this particular nitrogen and this particular bond together. This has, in this case, no strain at all, because one, we have to have 5 dihedral and we need to bring our 7 members together, while in this case here we have only 1 dihedral, but in this case we need to create a 3-membered. So therefore, in this case, for this reaction to be established, as we notice here, we have this particular reaction to be facilitated here, but then comparing our specific conditions here that are involved, not only in terms of enthalpy but also in terms of entropy, what we have is that this will cost entropy way more in here than in here. But in terms of the high strain that is accomplished here, what we see based on our condition is that, hey, the 3-membered ring is actually indeed greater than that of the 7-membered ring. However, in terms of entropy, the number of the dihedral bonds that we have to be rotated in order for this particular formation of the ring to be established, however, there's only 1 dihedral bond that has to be rotated, and therefore this is less entropy energy required compared to this particular side of the reaction right over here. So I hope you found this really interesting in terms of how stereochemistry of the formation of a bond is actually facilitated and important based on considering both the enthalpy and mainly focusing on entropy energy, where you're looking at the dihedral bonds that are rotated in alpha way to form rings from our specific chain containing a specific heteroatom that is present around that particular region. So on our next video here, we're going to be looking at reactions of saturated heterocyclic compounds, and this is where we're going to end off for this particular video. Hope you found this really informative. Please hit the comment down below. Let me hear your thoughts about this, but that way I can talk to you all soon. Stay smart as always and believe in yourself.